Section 4.2 is titled Linear Systems of Equations in Three or More Variables. In the previous section, we looked at systems with two variables and two equations. Okay, we used substitution, elimination, and we can also solve it graphically. However, in this section, we're going to add a variable, and therefore we have to have an extra equation. So the rule of thumb is if you have the same number of equations as you do variables, then you can solve the system and figure out the solutions for each variable. Okay, so what does a system of equations look like in three variables? Well, here it is. Looks a lot like two variables, but what we have is we still have a, but now we have three of them. Okay, and so we're calling a the coefficient of the x term, but we have an a1, an a2, and an a3. And so with the different subscripts 1, 2, and 3, these don't have to be the same number. We just use the same letter because it's the coefficient of the x. Then we have b, like the previous section, b1, b2, b3. And now our c's are going to be the coefficients of the z variable, our third variable. So we have x, y, z for the variables, and then here are all of the coefficients, a, b, and c. And then we have d1, d2, and d3 on the right hand side of the equation. Okay. And once again, in terms of the exponents of our variables, we have 1, 1, and 1 for all of the variables in these three equations. Alright, so this is the general form of a system of three linear equations. Here are some specific examples below in example 1. Okay, and this is not doing anything more than showing us some examples. What we could do is take a couple of them and write out the A, B, C, D for each. Here we have equation 1, equation 2, and equation 3. Alright. And so we can list all of the a's. We could say a1 is equal to 1, a Okay, so for the first system, we have a1 equals 1, a2 equals 2, and a3 equals 3. 1, 2, 3. We have b1 equal to 3, b2 equal to negative 1, and b3 equal to 2. C1 equal to a negative 2, C2 equal to 1, and C3 equal to a negative 3. And finally, our D's, D1 is 8, D2 is 1, and D3 equals 15. Okay. And so equation 1, 2, 3, all of our coefficients, and then the constants of the linear equations. Alright, so for the top three systems, A, B, and C are different systems. You can see we have all kinds of different numbers for the coefficients, different numbers for the constants. But in each one of these systems at the top, we have equations that contain all three variables, and even this one on the bottom row, D. Well, it turns out that you don't necessarily have to have all three variables in each equation. Okay. When that happens, what we do is we say that the A, for instance, in the second equation, okay, equation 1, equation 2, equation 3, A1 would be 1. There's a 1x here. In the second equation, we would say that A2 is 0. That's why the x has been canceled out. 0 times x is 0, and so there is no x variable in the second equation, and likewise A3 equals 0. Now for the b's, b1 equals -2, b2 equals 1, and then we do not have a y variable in the third equation, so b3 equals 0. And for the c's, all of our equations have a z, so we have a c1, a c2, and a c3. And then we have the d's. d1 is 9, d2 is 5, and d3 is 2. And so in chapter 4, we're going to be dealing with these throughout the chapter, and some in chapter 5. And so you just need to be familiar with these labels that we put on the coefficients and the constants for a system of equations with three equations. So example 1 is just meant to give you an idea of what these systems look like specifically. And so by a solution, we are looking for a triplet. Okay, it looks sort of like an ordered pair, but we can no longer call it a pair because we have 1, 2, 3 numbers. But we're looking for three numbers, an x, a y, and a z, that satisfy all three equations. So example 2 says we want to take 1b, and we want to test to see if this triplet is a solution to all three equations, and therefore a solution to the system. Alright, so let me go back up to the top and copy B down to example 2. We have 2 times x, and I'll leave a blank because we're going to fill in that x with a number. 5 times y plus 3 times z equals -18. The next equation, we have 3 times x plus 2. Then we have a minus z. Equals -12. We could say that the third equation has a 1x, then it has a minus 3y, so minus 3 and a blank, a space to insert our number for y, and then we have a minus 4 times our z equals -4. Okay, so what we want to do is take -1 and place it in the spots for the x. We take 2 and fill in the y's of each equation, and then -2 for z. Alright, so does all of this add up to give us a -18? Well, let's see. This would be a -2, Then we have negative 5 times 2. That would give us a negative 10. So far, negative 12. And then 3 times a negative 2 gives me a negative 6. And that does add up to give us a negative 18. So it works for the first equation, but these numbers also have to work for the second two. So we have to check those. 3 times a negative 1, 2 times 2 is a plus 4, and negative a minus minus 2 is a plus 2. Negative 3 plus 4 is 1, and 1 plus 2 actually equals 3. So no, this does not equal negative 12. Okay, and we can stop right there, because if these three numbers do not satisfy one of the equations, then it is not a solution to the system. Even if the numbers work for the third equation, they don't work for the second, so this is not a solution to the system. Alright, what about this next triplet? Okay, we want to, I shouldn't have erased that, but we've got a 2 minus 5 plus 3 equals negative 18. And we want to check a different set of numbers, negative 5, 1, and negative 1. So I'm just copying down this system, example 1b, and I'm leaving blanks, okay, parentheses for my x, y, and z. And here is our supposed solution. It says it is the solution, but we're going to double check it. So x is negative 5. Okay, x, y, z, alphabetical order for the triplet. 1 is y, and negative 1 is our z. So we're going to add all this up. 2 times negative 5 is a negative 10. 5 times 1, negative 5. And 3 times negative 1, negative 3. Check. We do get a negative 18. Next equation, we have 3 times a negative 5 gives us a negative 15. A 2 times a 1 gives us a plus 2. And then a negative times a negative 1 plus 1. And so negative 15 plus 3 does give us a negative 12. And finally, we have a negative 5. We have a negative 3. And then we have a plus 4. And the negative 5 and the negative 3 give us a negative 8. And if we add 4, it drops it down to a negative 4. So the third one checks out. So this triplet, negative 5, 1, negative 1, is a solution to the system. Okay, so from the examples above, we remember seeing, and this may be the same exact one, but we remember seeing an example of a system of equations where not all of the equations contained all of the variables. The first one contains all three, the second one contains a y and a z, and the third one contains only a z variable. Okay, this is what we call row echelon form. And when we start to solve these systems algebraically, this is our goal. Once we get them into this form with row operations, what we can do is called back substitution to figure out what the numbers are for x, y, and z that satisfy all three of these equations. Alright. So the procedure for back substitution is to take the equation with one variable and solve it. So if I divide both sides by 2 here, I figure out one of the numbers, z. Z equals 2. Okay. Now I take that result and I plug it into the second equation, which only contains 2 variables, a y and a z, but I already know what the z is. So I take the second equation and I plug in the number for z, and now I have another equation with only one variable. 3 times 2 is 6. Solve for y, subtract 6 from each side. Get y equals -1. So we have 2 of the variables. Now I want to know what number my x variable is, and that takes us back to the first equation. And I wrote down a third, so let me erase that. Equation 1. So we have x minus 2y. We just found out that y was -1. Z is 2. And that all adds up to give us 9. So once again, knowing 2 of the variables causes us to only have one variable missing in the first equation. So if I clean this up a little bit, I get x plus 2 plus 6 equals 9. And 2 plus 6 is 8. So if I subtract 8 from both sides, I get x equals 9 minus 8, which is 1. So my solution is 1, -1, and 2. Okay. If we had a 3-dimensional calculator and we were to graph these lines in 3 dimensions, then all 3 of these lines would intersect at this location. Okay, but with our TI calculators, we can only graph in our XY plane. Alright, so the system of equations is not going to be given to us all the time in the row echelon form. And so what we do is we do this Gibbs procedure, Gauss elimination with backward substitution method. Okay, we've already done the backward substitution, but what is Gauss elimination? Well, what we're doing is we're just taking 2 equations and 2 of the 3 that we're given and combining them with either addition. We don't multiply 2 equations together. We either add them together, or we take one equation and multiply it by a number, or we can just swap them around, as the first one suggests. Okay, in 2 it says we take one of the rows and we multiply it by a number, so all of the terms get multiplied by k, and that creates a new row. Or we could multiply a row by a number and add it to a second equation, and when I say row, I'm talking about equations. We can multiply one row, add it to another row, and get a new row. Alright, so that's sort of vague, and to really give you a sense of what I'm talking about, we'll work example 4. And this is just a system of 2 equations and 2 variables. We already know that we can solve this with elimination and substitution, but we want to learn this new way, this Gauss elimination. Okay, so what we do is, and this is sort of the same thing as elimination. Okay, but what we're going to do is we're going to write the row that we want to replace on the right. Okay, we're going to use these double-ended arrows, And so what I want to do is eliminate the x. Okay, I want to eliminate the x on the bottom row, so I'm going to replace row 2. So I put it on the right. So now, let's see, I don't think I gave myself enough room here to write out what we actually need to do. I'm replacing row 2, and whatever I replace it with, I want it to only have one variable, and the one that I'm going to eliminate is the x. And so to do that, what I need to do is take row 1 and multiply it by -3. If I just focus on the x, if I take the x term and multiply it by -3, that would give me a -3x, and then if I added it to the second row, then I would get a resulting equation with no x variable. The -3 here and the 3x in the second row would cancel out and leave me with 0. Okay, whatever I get from performing these operations, I'm going to replace row 2 with that. So here is our Gauss elimination operation. And so what do I actually get by doing that? Alright, I'm only replacing row 2, so what I can do is just go ahead and copy down the first row. Nothing's going to change about it. And so to carry this out, what's going to happen with my x? Well, I take -3, I multiply it by the coefficient of the x in row 1, R1 right here, and then I add the number from row 2 in front of the x, 3, and I get 0. And that gives me my brand new row 2, which will be 0 times x. What about for the y variable? Or you could write b's here because we're using the coefficients. Whichever makes more sense to you. It doesn't really matter. Here we're just sort of combining the a's. Alright, what about the b coefficient of the second row? Well, we take the b of the first row, which is -3. We multiply it by -3, and then we add the b of the second row, which is a +2. And what do we get? We get a -9 plus 2 is -7. And so this number is going to take the place of b in the second row. We have a -7y. And now what about our c? Okay, with only two variables, we call this constant on the right hand side of the equation a c. So here's my operation. This is what I do for all the coefficients and the constants. I take -3, I multiply it by the 7 from row 1, and then I add what's in row 2, a -1. Actually carrying out this calculation gives me a -21, and then -1, a -22. And so this number replaces my c in row 2. Okay, so this is our new system, which is just a different version of the one that we started with. Alright, having a 0x in the second equation means that I no longer have an x variable in that equation, and so at this point we're ready for back substitution. I take this equation, trying to write this neat, -22, there's not a z there, I thought that was a z. Okay, negative 7y equals negative 22. So to solve for y, divide both sides by negative 7, and I get one of my variables. And I only have two. So we have 22 over 7. So I took my equation with the one variable. I figured out what that variable is, the number for it, 22 over 7. And now I just plug it back in the one above it, equation 1. And so I get x minus 3 times 22 over 7 equals 7. Alright. What is this 3 times 22 over 7? Let's see, we get 66 over 7 equals 7. Definitely not a pleasant number to work with. To solve for x, all we would do is add 66 over 7 to both sides, and the 66 over 7 would cancel, and we'd end up with 7 plus 66 over 7. If we were to find a common denominator for the 7, well, that would be 7. So 7 times the 7 on the top would give us 49. And so in the end, x ends up being, what do we get? 106 and then plus 115 over 7. Okay, so sometimes the numbers don't work out to be very pleasant, but in this case we got fractions. But this is how you would use the Gibbs method. You do row operations until you get it to row echelon form. Okay, each successive equation has one less variable, and you start with the equation that only has one variable and you work your way backwards. Okay, substituting in the numbers that you find along the way until you have all of the variables. Alright, so now we have one with three variables and three equations. So things could get a little messy. So what we're going to do first, and we can use the same procedure for all of these systems, we will take the first, or I'm sorry, we'll take the bottom two equations, and we'll combine them until we get, we'll rule out one of the variables. We'll rule out the x variable. Okay, we'll eliminate it from one of these bottom ones. And we want to do that for both the second and the third. Alright, the easiest way to do that is to use the first equation, because we don't have a number, we have a 1 in front of this x, so we can easily change it to a -2 or a -3 to get rid of these x terms in the bottom two equations. So I will say -2 times r1, that'll give me a -2x for equation 1. I'm going to add that to r2, and then I'm going to replace r2 with whatever we get from these operations. So the other equations, only on the right here, I'm only showing which row that I'm replacing, which equation, the second one. The first and third are going to stay the same. Alright, so we're going to carry out this operation and figure out what we put here for the second equation. Alright, for A, I take -2 and I multiply it times the A of row 1, which is 1, and I add row 2, which is 2, and I get 0. Okay, that was the whole purpose of carrying out this operation. So there will not be any x variable written in equation 2 now. But we have to figure out what the other numbers are going to be, the b coefficient. So we take negative 2, that's our operation, and then we take the b coefficient from the first row, which is 3, and we add row 2, the b of row 2 is negative 1, so we subtract 1. We get a negative 6 minus 1 is a negative 7. And so we can go up here and for the second equation write negative 7y. Alright, for the c coefficient we have negative 2 times the first row a negative 2 as well. And then we add the c coefficient of the second equation, which is 1. Negative 2 times negative 2 is 4, plus 1 is 5. Okay, and don't forget about the d, the constant term in the equation on the right hand side. Negative 2 again times the d of the first row, 8, plus the d of the second equation, 1. Negative 2 times 8 is a negative 16, plus 1 is a negative 15. Alright, so we've done some operations with our rows. We've knocked out an x on the second equation. We're one step closer to the row echelon form. Now, I'm going to take this system and perform another operation on it. And I'm going to replace row 3. Okay, so I've eliminated the x from the second one, and now I want to eliminate the x from the third one. So I'm going to replace row 3. And what I need to do is take my first equation, r1, and multiply it by a negative 3 and add r3. So if this is a negative 3x and I add it to r3, a 3x, then I'm going to knock out the x in this third equation. Alright, not doing anything to, I'm using the first one, but I'm not changing anything about it. I'm only replacing row 3 or equation 3. Row 3 and equation 3 are the same thing. Alright, so I don't want to write anything for 3 because I'm going to replace it. And now I go through this operation for A, B, C, and D. Alright, so my operation calls for a negative 3 times row 1, which is 1. And then I add row 3, which is 3, and I get 0. So there will not be an x term here in the third equation. For B, I have a negative 3 times row 1, which is 3, and I add a 2. So negative 9 plus 2 is a negative 7. Alright, for the z coefficient c, I have negative 3 again. That just comes from this operation that I had to do to get rid of the x. So negative 3 times a negative 2 from row 1, and then add row 3, which is a negative 3. And what do I get? Negative 3 times negative 2 is a positive 6, minus 3 gives me a positive 3. So this would be plus 3z. And then for D, I have a negative 3 times an 8 plus 15. Negative 3 times 8 is a negative 24, plus 15 would give me a negative 9. And so we sort of completed the first step. And you can use the same procedure for every one of these systems of equations. So 2 steps, and we have now eliminated the x from the bottom 2 equations. Alright, we only have one more step. We want to eliminate the y from one of the bottom 2 equations. Okay, and we can't do that with the first equation because it has 3 variables. And so if we use the first equation, then we're actually going to end up with an x back in one of these bottom 2. So we want to take these 2 and combine them in some way to where one of the variables cancel. Alright. If we take row, let's see, I'm going to replace row 3 because that's usually the line that we have the equation with one variable. And what I'm going to do is I'm going to take negative r2 and add it to r3. Because if I make this a positive 7, which is what a negative will do, minus a minus 7 is a plus 7, and then I add it to the negative 7, I'll get a 0 coefficient for the y. In other words, the y variable will disappear for my new row 3. Alright, so equation 1 and 2 stay the same. We have x plus 3y minus 2z equals 8. Negative 7y plus 5z equals negative 15. And now I want to replace row 3. So a, well, we don't have an a, so that would just be negative 0 plus 0 equals 0. Row 2 and 3 do not have an a coefficient. What about b? Here we have a minus. The b for row 2 is a minus 7. And then I add row 3, which is a minus 7, and I get 0. Minus minus 7 is plus 0. Plus 0 minus 7, 0. So I'm not going to have a y term here. C, the z coefficient, I have a negative 5 for row 2, and then I add row 3, which is a plus 3, and I get negative 2. And finally, what about D? Okay, I have a negative row 2, which is a negative 15, and then minus 9. This is a positive 15 minus 9, so I get a 6. And we have now arrived at row echelon form, and I can use bag substitution from here to figure out what my x, y, and z are. It's going to take a little space to do that, so I'm going to have to erase some of this stuff. And at this point, we don't really need anything but this system. Okay, this is just a different version of the original system. So I take my third equation and I solve it for z. That gives me z equals a negative 3. Now I take my second equation, and I have two, sorry, I'm looking at the original one. I don't want to do that. This second equation, I have negative 7y plus 5, and I insert the number that I found for z here, negative 3, and that equals negative 15. So this is negative 7y minus 15 equals plus 15. If I add 15 to both sides, I'm one step closer to getting the y by itself. So negative 7y equals 0, and so y equals 0. I've found my second variable. And so finally I take equation 1, and I have x plus 3 times y, which is 0, minus 2 times z, which is a negative 3, and that equals 8. So I have 0, negative 3. 0 times 3, that knocks out this middle number, and so I'm just left with a negative 2 times a negative 3, a plus 6. If I subtract 6 from both sides, I get x equals 2. And I have a complete solution now. I have my x variable, my y, and my z. This triplet is the solution to this system of equations. Alright, the next one, what I'm going to do, I like to have the x with the coefficient of 1. I want to use that to eliminate the x's in the other two equations. So I'm going to do a row swap. I'm going to take row 3 and I'm going to swap it with row 1. Alright, I'm going to do something else too. I'm going to write this in a different way. Row 1, I swap row 1 and row 3. Okay, what you can do if you want is just copy down the numbers or the coefficients. We can say 1, negative 3, negative 4 equals negative 4. Okay, and avoid writing the variables. The variables are still there. We just didn't write them. Okay, it just saves us a little work. And now I take row 1 and I put it in row 3. And row 2 stayed the same, so 3, 2, negative 1 equals negative 12. Alright, this is just going to save me a little work. So now that I have my 1 in my top row, I'm going to use it to eliminate the 3 and the 2 of the second and third equations. So negative 3 times R1 plus R2 will give me a new R2. The only equation I'm changing is R2, so I can just go ahead and copy down 3 and 1. Okay, for A, I have negative 3 times row 1, A, plus row 2, 3. Well, that equals 0. I'm not going to get an x term here. Negative 3 times negative 3 plus 2, that equals 11. C, I have a negative 3 times a negative 4 plus a negative 1, and that gives me an 11 again. Okay, positive 12 minus 1. And for D, I have negative 3 times negative 4, let's see, and then minus 12. So this is positive 12 minus 12, 0. Next, I'm going to eliminate the x from the third equation. So I need a negative 2 times r1 plus r3. The first and second stay the same. I replace the third, so I need to do the calculations. I have a negative 2 times a 1 plus a 2 equals 0, so no x term for the third equation. B, I have a negative 2 times a negative 3 minus 5. Negative 2 times negative 3 is 6, minus 5, I get a 1. R1, what do we have? That is a negative 4 for C, and then I add 3, and I get 11. And then finally D, we have a negative 2 times a negative 4 minus 18. Negative 2 times negative 4 is 8, minus 18 would be a negative 10. And now for our final step, we've eliminated the x in the last two equations, and now we want to take the last two equations and eliminate the y from one of them. Okay, let's see, I'm going to use the second one to eliminate the 1 from the third one. Okay, if I just add these, I get a 12, and that doesn't cancel this y term. Okay, so if I multiply row 2 by negative 1 over 11, then this would become a negative 1, and a negative 1 would cancel the 1 in the third equation. So nothing's going to change about the first and second equations, only the third. And so now I have A is negative 1 over 11 times 11 plus 1. That gives me a 0. So no y term here in the third equation. B, I have a negative 1 over 11 times another 11, and then that is plus 11. Okay, row 3 was 11 in the previous system. So I have a negative 1 here plus 11, that will give me a 10. And then C, I have a negative 1 over 11. Oh, okay, hold on, I mixed my letters up. This is actually B, and this is C, and this is D. Okay, there were no A coefficients in row 2 and row 3. They were just 0. So no need to calculate that. I wouldn't end up with an x term. So for D, let's see, negative 1 over 11 times 0, and then plus row 3, which is negative 10. This is 0, and so I just end up with a negative 10. for D of the third equation. And so here we have row echelon form. I can throw away all of this other stuff. I don't need it anymore. This, okay, we dropped the variables, but this with the numbers is equivalent to x minus 5y minus 4z equals negative 4. 11y plus 11z equals 0, and then 10z equals negative 10. Alright, all we did is insert the variables back in their places, and that saved us some time from having to write out these variables in every step. So I take the third equation that only has one variable, I solve it for z, and I get a negative 1. I take the second equation, and I replace the z with a negative 1, and I get 11y equals, hold on, sorry, getting ahead of myself. I get 11y minus 11 equals 0. Add 11 to both sides. I get 11y equals 11, which gives me a 1 once I divide both sides by 11. And so finally I'm back to the first equation, which is x minus 5 times my y, which is 1, minus 4 times my z, which is a negative 1, equals negative 4. This ends up being minus 5 plus 4 equals negative 4. Negative 5 and 4 is a negative 1. And if I add 1 to both sides, I get a negative 3 for x. So my solution is negative 3, 1, negative 1. And if you write it as a triplet this way, you have to put it in the right order, x, y, z. Okay, the last page. Okay, so what's happened here is I started working this problem out, and I didn't even realize that it wasn't recording. So without erasing any of this stuff, I'm just going to walk back through it and explain what we did here. So we started out with this system of equations, and on this page what's going to happen is we're going to end up with two special situations. One of these systems is going to have infinitely many solutions, and the second one is going to have no solution. Well, it turns out that this one is the case where we have infinitely many, because the third equation ends up having a number equal to itself. 0 equals 0. So how did we get to this point? Well, I started out, same procedure as the previous two problems. We want to eliminate one of the x's from the, well actually we want to eliminate the x's from the bottom two equations, 2 and 3. But we can only do one at a time. So I eliminated the 5 first, and the way I did that is I multiplied the first row by -5 and I added the second row, which is a +5, and it canceled out the x here. So if I go back through this operation with the numbers, coefficients, a was -5 times 1 plus 5. That gave me a 0 here. For b, where did this -2 come from? Well, I had a -5 times the system from the previous step had a 2 in the place of b for row 1. Okay, row 1 times a -5, then plus row 2, which is a +8. -10 plus 8 gives me the -2 that I have written here. C, once again, -5 times a -2 from the first equation, and then -6 from the second one. I end up with a -10 end up with a +4. Have a +4z here. And then for D, we had a -5 times the 3 plus a 14 gives me this -1. Alright, and the first and third equation stayed the same. We only replaced row 2. Alright, that brought me to this point, and so now I want to get rid of this 3x. I want to knock out the x from the third row. So I said the first row times -3 plus the third row replaces the third row. And that's going to give me this system. So if I work out the A, B, C, D, I'd start out with, let's see, no longer using -5, so I just had to rewrite all of this. -3 times 1 plus 3 equals 0. And so down here we have nothing here in row 3 for the x term. The x term disappears. For B, we have -3 times 2, and then plus 4 gives me a -2. And then -3 times the C, which is a -2, plus or minus a 2, equals a +4, which we have written right there. And then for D, referring back to this system, we have -3 times 3, row 1, and then plus 8. Ends up being a -1, and we place that -1 here. Now, that has taken us to this system here in the middle. Well, at this point, it's obvious that the second and third equations are identical. So what we do at this point is we say row 2 minus row 3 replaces row 3. If we do that, we get -2y plus 4y equal -1 minus a minus 2y minus a 4y minus a minus 1. Okay, this is row 3 times a negative. This just ends up, the minus minus is plus, and this one would end up being a plus. And when we add these, they just cancel out. Everything cancels out and gives us 0 plus 0 equals 0. No need for two zeros here. In the third line, we put 0 equals 0. So there are infinitely many solutions, but not every combination of three numbers is going to be a solution. So we need to figure out the specifics of the x, y, and z. And so what we do is we pick a what we call a parameter. We don't need any of these other systems now. What we do, we still start with the third equation, and we say z equals a particular number. We'll say a. We don't, z could equal any number. But we're solving for the solution in general. So z could be any number. We're going to rename it and call it a. Well, if z is a, what does y turn out to be based on a? We take the second equation and we write negative 2y plus 4 times a equals negative 1, and we're going to solve this for y. So we would get negative y, or negative 2y, equals, to get rid of this term for a, we subtract it from both sides. And so we'd have a negative 1 minus 4a, and then we divide by a negative 2 to get the y by itself, and we'd end up with, let's see, if we divide negative 2 into both of these terms on the top, we get a positive 2a plus a half. And so this is our y. This is our z, a. And so x, y, and z are all going to depend on a once we're finished. Now we take 1 and we say x plus 2 times 2a plus a half. Okay, we replace the y with this expression, and then we subtract 2a. Z gets replaced with an a, and that equals 3. Two times 2 is 4. 2 times a half is 1. Combine the like terms. Okay, and now we just move the 2a and the 1 to the right. Subtract 1 from both sides. 3 becomes a 2. And then we have a minus 2a. And so here is our expression for x. 2 minus 2a. Y is 2a plus a half. And then z is an a. This is our general solution to this system of equations. This is what happens when there are infinitely many solutions. So you can pretty much guess that the next one is going to be the situation where there is no solution. Alright, we're going to swap these two rows. That'll give us this system: x minus 2y plus 3z equal 2. Second row stays where it's at. Yep, I want a 3x. So I swapped them, first and the third, and now I want to start with my row operations, getting rid of the 2x and the 3x. I'll start with the second row, getting rid of the 2x in the first step. That's not going to change the first equation or the third one. So how does the a coefficient work out? Well, it's supposed to work out to be 0. Okay, negative 2 times 1 plus R2, 2, does equal 0. So we do not replace row 2 x term. There is no x term here. Negative 2 times the b of R1 would be negative 2 times this negative 2 plus a negative 3, which is the same thing as subtracting 3. We get a positive 4 minus 3, a 1. So in row 2 we just put a y. For the c coefficient we have negative 2 times a 3 plus a 1 ends up being a negative 5. And then for d we have negative 2 times a 2 plus a 1. That gives us a negative 3. Okay, just double checking my work. Definitely don't want to make a mistake in the beginning and then get to the end. Okay, so here's our system at the moment after performing this Gauss operation here, if you want to call it. Now we want to get rid of this 3x. So I say row 1 times a negative 3 plus row 3. And that replaces row 3. Row 1 stays the same along with row 2. So we start with the a coefficient and we say negative 3 times 1 plus 3 equals 0. For b we have negative 3 times a negative 2 plus a negative 4, which is the same thing as minus 4. We get a positive 6 minus 4 is a 2. For c we have a negative 3 times a 3 minus a 1, and we get a negative 9 minus 1 is a negative 10. And now d, we have a negative 3 times, what do we have? A 2 plus a 1. That gives us a negative 6 plus 1 is a negative 5. And now, to get the last step, to row echelon form, we combine these equation 2 and 3 to cancel out a y. So what I'm going to do is say negative 2 times row 2 plus row 3, and that's going to replace row 3. So for a, well, we don't want to do a because there is no x term, so there is no a coefficient, it's just 0. So we'll start with b. Negative 2 times row 2, which is 1, plus 2 gives us 0. So there is no y term here. For c we have 2, negative 2 times a negative 5 plus a negative 10, which is the same thing as minus 10. We get 0. So no z term either. But we'll write at least 1 0 over here on the left side. What about our D? We're still performing this operation. We have a negative 2 times, let's see, a negative 3 minus 5. Negative 2 times negative 3 is a positive 6, minus 5 is a 1, and so we get a 1 here. 0 does not equal 1. Here's our row 3. 0 equals 1, and that is not true. So this is much easier than the last situation. At this point, we declare that there is no solution. So I would argue that this is our favorite type of linear system of equations. And that completes section 2 of chapter 4. Thanks for watching.